So today we will discuss about more important part of application of eigenvalue and eigenvector in order to find eigenbasis and diagonalization. So there is a very mutual interesting kind of relation between getting an eigenbasis and diagonalization of a matrix. Generally, whenever I am talking about finding eigenvector and eigenvalue of a matrix, then we used to find a square matrix. We are not going for non-rectangular rectangular kind of matrix, that means m by n kind of matrix. Generally we are going to find eigenvalue of n by n matrix, and if you are taking m by n matrix, any rectangular size matrix, then that time we will talk about singular value decomposition, and that one is having a different theory. That concept I will discuss in detail tomorrow. Coming to outline of today's lectures, first I will give a recap of the process, that algorithmic approach to find eigenvector, and also we will solve few problems. And after that, I would like to discuss about eigenbasis. It is very important in order to get one another concept to get a basis. So till now you had already seen that how to find basis. Simplest basis happens to be a standard basis. Otherwise, you need to get non-standard basis by satisfying the criteria of being a basis. Otherwise, one more concept, once you are having non-standard basis, then you can apply Graham-Smith orthogonalization in order to get orthonormal basis. So those things you had already seen regarding basis. Now that we will learn new way to get another basis, that we are calling it eigenbasis with respect to eigenvector. So that's why I told that it is very important part of this lecture. And once we are having idea of eigenbasis, then I can talk about diagonalization, because the idea of having eigenbasis is giving a visualization of big diagonalization of a given matrix. So all whatever I'm putting in order, there is always a meaning. So coming to recap of finding eigenvectors. So in last class we had already discussed. So here I am taking one more example. It is a 3 by 3 matrix. You can see that. Uh, due to size of being 3 by 3, you can say that this matrix will have at most 3 real eigenvalue. So I have already mentioned that I will be interested only at finding uh, real eigenvalue and the corresponding eigenvector. So we are not interested here in this course to find the complex eigen value or complex eigenvector. That one is part of advanced linear algebra or something like that. We are not going to cover that. So at most 3 eigenvalue will 3 real eigenvalue will introduce here, and we can get at most 3 eigenvector as well. So real. So in short, I'm writing it E V. Okay. So how to find? So there is a step I had already discussed in first step. What we will do, we will find a characteristics polynomial of this given matrix. So characteristics polynomial, just how we find? We finding the determinant of the newly designed matrix A minus lambda times A. It is not kernel. Just we are finding determinant of A minus lambda time A, and when you will solve this determinant, it will be converted into a cubic polynomial, and further cubic polynomial you can easily factorize into a linear polynomial. So lambda times lambda minus 1 whole square. That means you observe 2 eigenvalue. One is 1, another eigenvalue is 0. And what is the algebraic multiplicity of 1? Algebraic multiplicity of 1 is 2. Why? Because 2 is coming 2 times as a root of this characteristics polynomial. So that's why 1 is having algebraic multiplicity 2. And what is the algebraic multiplicity of second eigenvalue 0? That one is 1, because 0 is coming as only one time. So that's why algebraic multiplicity of 0 is 1. Now once we are having eigenvalue, then we will go to find eigenspaces in second step. So how can we find eigenspaces? It is eigenspace with respect to first eigenvalue lambda 1 equal to 1. We are calling it, either you can denote it by e1 or you can call it lambda e1, e lambda 1. Both notation are valid, there is no issue. So what is this eigenspace? It is talking about kernel space of A minus I, the matrix A minus I. So it is all, you are having already a idea how to find kernel space of a given matrix. So this is, you know, new matrix you are having with respect to lambda equal to 1. You are having A minus I, and you need to find kernel space of this one. So kernel space of this one is just what it is equivalent to solving this homogeneous system of linear equation. Once you will have this homogeneous linear system, so just you can observe here, you observe that here what first column is not a pivot column, it is a non-pivot column. Why? All the entries in the first column are zero. But if you come to see in second column is the first nine pivot column, and third column is also the pivot column, because all these are coming in a standard unit form. So that's why we can say that x1 is here free variable, but x2 and x3 are dependent variable. So due to that, x1 will take value freely, and x2 and x3 are fixed or dependent. So that's way we can say that kernel space of this a minus I, that means eigenspace e1, it is a linear span of single vector 1 0 0. That means you got a line with respect to eigenvalue as a eigenspace. So first eigenspace you have already got. Second eigenspace with respect to lambda 2 equal to 0, how you got? You have to do in the similar fashion. So in short, again I would like to denote this eigenspace by E0, because it is associated with the eigenvalue 0. So I will call it this eigenspace E0. So again it is similar to find solving this system of linear equation. So if you come to see in this reduced form, if this system is already in reduced form, so we can observe that first column is an pivot column. Second column is what? Second column is not a pivot column, because it is repetition of just first column. And second column is not a pivot column. And third column, it is again a pivot column. So you can say that x1 is your dependent variable, x3 is dependent variable, but x2 is what? It is a free variable. So x2 can take any value freely. Depend upon that, after just getting the solution space of this system, that means equivalently you can say that kernel space of a plus 0 times I, it would be nothing, just it is a linear span of this vector minus 1 1 0. That means again you are getting E0 is what? It is a line with this direction or this basis and direction both correspond to each other, there is no difference here. So in linear algebra, direction is a concept of geometry, and basis vector, it is a concept of linear algebra, you can say that. So you have already got both eigenspaces E1, that means with respect to first eigenvalue 1, and E naught with respect to second eigenvalue E naught 0. So you can claim that this basis, it is a first, you can say that it is first eigenvector, and the second basis element of this basis element of E naught, you can call it is second eigenvector. So why I am calling this one especially these are actually eigenvector. You know that if you take any linear combination of this basis element, that would be again a eigenvector. That means it will preserve the direction of that. If you take you can verify this one, it is a homework. If you multiply matrix A with V1, then what you will get? Definitely you will get lambda 1 times V1. That means you will get equal to lambda 1 equal to 1. So you will get K1 times V1 equal to V1. Now, similarly, if you take any scalar multiple of this, call it alpha times V1. So V, you are taking any scalar multiple of this one. So if you multiply matrix or operate matrix over this one, so what alpha is a scalar, so it will just come out, and you will get to know that uh, a times alpha v1 equal to alpha v1. So again, so you can say that alpha v1 is also, and it also not changing the direction when we apply a over this one. So that's why alpha time v1 is also a eigenvector of a with eigenvalue 1. So similar, so that's way. So the simplest form of eigen vector happens to be the basis element of that corresponding eigenspace. So that is the main concept. Similarly, if you come to see that here, if you just it is a, you can consider this one as a homework. You can verify, apply matrix A over second vector, this basis vector v2, and you will come to see that multiple of this one would be what? It would be 0. Why? So 0, you can write it 0 times v2. Why? Because we know that this eigenspace we got with respect to eigenvalue 0. So that's why everything becomes decomposes, or there is a reduction in the dimension, you can say that. And also similarly, if you take any multiple of v2 and multiply a over this one, then again that matrix alpha times v2 will be nullified due to when you apply this matrix a over this one, so it would becomes 0. So further you can say that it means that 0 time alpha v2, you can say that. So those are the concept to visualize eigenvector and the process of finding eigenvector. Now we are coming to see a second example. So again I am taking here 3 by 3 matrix. This one is the 3 by 3 matrix. So we had already seen that what are the eigenvalue and what are the eigenvector. We have already seen that. So we can check that these vector are actually eigenvectors. So verification I have already done in the previous page. So this is the verification part. So if you multiply matrix over this kind of vector, you will get the same vector. That's why it say that 1 0 0 is one of the eigenvector of this matrix. So that means it is, we are calling it v1, and v2 it is basis of the second eigenspace e0. So that one is also eigenvector. When this one is a step 3, you can say that it is a validation part or verification part. So you try to validate it here. So validation, you do here validation or verification. Validation step, you can call it like that. Okay. So you can observe that if you multiply this matrix over this one, you are getting the same matrix. Same vector. There is no change in the direction. Yeah, it becomes 0. Why? Because eigenvalue is 0. And geometry, if you want to visualize geometrically these eigenspaces, you can see that this one is eigenspaces corresponding to eigenvalue 1, at that we are calling it E1. And so it is a just a line, because having basis in there is only one basis, that's why it is a line. And E naught, that means eigenspace associated with eigenvalue 0, it is again having single basis, that's why we are getting another line. So we are getting two line in R3. So it is in R3 because it is, the matrix is 3 by 3. So that's why 3 by 3 matrix always define a linear transformation or operation from R3 to R3. It is a 3 by 3. So that's where we are getting this concept. So I have already expressed geometrical interpretation of the corresponding eigenspaces. Now coming to one more important concept of multiplicity of a eigenvalue, that we are calling it geometric multiplicity. It is associated with directly eigenspace, dimension of eigenspace. So till now we had already seen that how to find eigenspace with respect to a given eigenvalue. So consider we are having an eigenvalue lambda of a given n by n matrix A. Then the dimension of eigenspace E lambda. That means E lambda is what? It is an eigenspace, or simply you can say that it is a kernel space of A minus lambda I. So dimension of this eigenspace, we are calling it the geometric multiplicity of eigenvalue of lambda. And we have already seen before that algebraic multiplicity of lambda. So what is the relation between geometric multiplicity and algebraic multiplicity? So geometric multiplicity is always less than equal to algebraic multiplicity. So this kind of relation you will observe that. And when there is a case of diagonalizability, and equality will come. So, so you can say that geometric multiplicity is less than equal to algebraic multiplicity. This is the relation between these two multiplicity of an eigenvalue. So now onward, what you do, once you are having idea of both multiplicity, keep on calculating both kind of multiplicity. So one way to establish diagonalization is just purely based on this multiplicity. If you calculate these two multiplicity and you come across to see that these two are equal, then you can simply claim that that matrix is diagonalizable. But even it is not giving a better visualization of things. So I would like to avoid. So thus the geometric multiplicity is the nullity. We can say that the nullity of the matrix A minus lambda I, or simply using uh, theorem of fundamental uh, first part of fundamental theorem of linear algebra. You can say that geometric multiplicity is nothing, just it is n minus rank of A minus lambda I. So that way also, because there are various way to find rank. So easily you can find rank and directly you can get geometric multiplicity. So it is a pure algebraic approach, pure algebraic approach. Now consider a matrix. For example, I have taken a matrix, same matrix what previously I discussed. So having first row 1 1 0, second row 0 0 1, third row 0 0 0. Now then, what is the first task? We will find the characteristic polynomial of this one. So characteristic polynomial of this one is what, determinant of a minus lambda I. And if you simplify, you will come across to see that characteristic polynomial is lambda times lambda minus 1 to the power 2. So this is the criteria, very nice characteristic polynomial. From here, easily we can get eigenvalue. What are the eigenvalue? It is having two eigenvalue. One eigenvalue is, we are calling it lambda 1 equal to 1. Another eigenvalue is 2. Lambda 2, that one is 0. So we are having two eigenvalue. Now we can calculate what is the algebraic multiplicity of 1. So I will write in short k dot m dot of uh, first eigenvalue 1 of lambda 1 equal to 1. So what is that? It is 2. Similarly, what is algebraic multiplicity of second eigenvalue? That is lambda 2 equal to 0. That one is 1. Algebraic multiplicity of lambda 2 equal to 0. That means second eigenvalue, it is 1. Now, we will in next step we will find corresponding eigenspaces. So what is E1? That means eigenspace associated with eigenvalue 1. E1 is what? It is a one dimensional subspace, that means it is a line. And E2, that means or you can call it E0. E0, that means eigenspace associated with the second eigenvalue 0. Again we observe this one is a line. So how many, what is the dimension of E1? Dimension of E1 is uh, 1, because it is having only one basis element. So that's why dimension of E1 is equal to 1. So we can say that here it is 1. We can say that geometric multiplicity, that means in short I will write it g dot m dot of eigenvalue lambda 1 equal to 1 is what? It is the dimension of eigenspace E1. And what is the dimension? Dimension is 1. And definitely we can observe that this one is less than corresponding algebraic multiplicity, because algebraic multiplicity we can observe that it is 2. So it is less than algebraic multiplicity of eigenvalue 1. But again here, if you come to see E naught, then what is the dimension of E naught or E0? That means eigenspace associated with eigenvalue 0. So dimension of E0 is 1. Here we observe that algebraic multiplicity of 0 and geometric multiplicity of 0 both are equal. So here we observe equality equal to algebraic multiplicity of lambda 2. So here we equality observe with respect to both these two kind of multiplicity of algebraic geometric multiplicity of lambda 2 equal to algebraic multiplicity of lambda 2. So this equality we observe, but we don't observe here such equality in case of lambda equal to lambda 1 equal to 1. Okay, so we have calculated everything here. Now coming to another important concept that we are calling it eigenbasis. So what we do here, we will try to find a new important basis that with the help of eigenvector. So first I would like to introduce what is eigenbasis. So consider we are having n by n matrix A, and then a basis of domain of space Rn, which is consist of eigenvectors of A. Then we will call that basis eigenbasis for A. Why for A? Because that eigenbasis is coming due to A. So that's why we are saying that eigenvector the basis consisting of eigenvector of A is actually an eigenbasis of A. So remember that every matrix is not having eigenbasis. So few matrix may have, few may not. So that is the criteria. So we will try to look for a special kind of matrix which will have eigenbasis. So in order to visualize eigenbasis, I am revisiting the previous example, orthogonal projection. So consider orthogonal projection in R3, that means where we project uh, any three-dimensional vector to a plane. So that we denoted Tx equal to Ax. So Tx, you can say that it is in the geometrical transformation, you can say that T of X equal to projection of any three-dimensional vector over plane V, like this way. So definitely you will get a matrix of this projection transformation. That matrix I denoted A. So A is the matrix projection matrix. Simply you can say that it is a projection matrix. And if you are willing to find eigenvalue and eigenvector, so easily you can find that if you take any vector from the V, then what is the projection of V? Projection of V would be the V itself. If you are taking any element V from, so same thing I have discussed many times. So if you are taking any element from subspace V, or that means plane V, then projection of V would be projection of V with respect to subspace V would be the V vector V itself. So it simply say that V is actually an eigenvector. That means it is having relation like this way, that projection matrix time V equal to V. It implied. Okay, N implied by as well. So that's way, yeah, any vector on this plane, if you take any vector on this plane, call it this V. So this V is what it play as an eigen vector for the given projection transformation or given projection matrix. So what we will say that, we will say that uh, what what is the scalar here coming? A scalar is coming lambda 1 equal to 1. So a scalar time, that one is the, so V is a eigenvector for this projection matrix. V coming from the plane, this plane V is a eigenvector with eigenvalue 1. Eigenvalue 1. So that's way you are getting first eigenspace E1 is equal to the given subspace V or plane V itself. And then what is the another kind of eigenvector? So if you take any vector from orthogonal complement of this plane. So orthogonal complement, that means it will be perpendicular to this plane. So it will come from like this way. So call it W kind of thing. So if you take any vector which is perpendicular to this plane, and if you apply a matrix over what is the projection? That means this operation projection matrix over this one. So what would be result? So projection of W with respect to this plane would be what? It would be projected back to where? It will be projected back to the reference point or origin. This is your origin, reference point origins. That's way you are getting orthogonal complement of B is actually second eigenspace which is coming with respect to this second eigenvalue, because we observe every vector in this orthogonal complement, it becomes, it map to 0. So you can say that 0 is nothing, it is what? It is 0 times W. So that's where second eigenvalue is lambda 2 is 0, and the eigenvector is any vector on this orthogonal complement. So that you can visualize these two concepts. Okay, so what concept here, what is eigen basis here? So V is a plane. So plane definitely, when you say plane, definitely it will have two bases. So consider V1 and V2 is the basis of the given plane V. So that's why we are able to write V as a linear combination of V1 and V2. Okay, linear span of V1 and V2. And what is V per? V per, it is a line which is perpendicular to this plane. So then line is having single direction. So suppose that basis V3 is the basis of this line V per. So now we are having uh, three three different kind of vector. We concate these three in together. So V1 and V2 are coming from uh, eigenbasis eigenspace E1. Then we take basis of eigenspace E naught, that is what, V3. So now we are having three set of vector, and we know that this projection, orthogonal projection, it is a operation from where to where? It is a linear operation or linear transformation from R3 to R3. And R3 need how many basis element? It needs three basis element. So these eigenvector actually it will form a basis of, it form a basis of R3, and this special basis is actually coming as an eigenvector. So that's why we call this basis eigenbasis of R3. So one eigenbasis you got with respect to orthogonal projection. So interesting relation, you will see that the V3 would be always perpendicular to V1 and V2. Okay. I'm taking one more example, simple example, that 2 by 2 matrix it is having entry 1, first row is 1 2, second row is 4 3. So again, just calculate eigenvalue of this one. So eigenvalue of this one is having two eigenvalue. I have a skip process of finding eigenvalues. First eigenvalue is 5 and second eigenvalue is -1. So second eigenvalue is -1. You can easily calculate it. It is just a 2 by 2 matrix, so you can calculate it. So you got second eigenvalue. So find then first eigenspace E5. That means eigenspace with respect to eigenvalue 5. It is nothing just kernel of matrix A minus 5 times I, and it is coming as what? It is just a line linear span of this vector 1 2. Similarly, you can get eigenspace with respect to second eigenvalue -1, and that we are calling it E minus 1, and it is nothing just, it is a kernel space of A plus I, matrix A plus I, and if you simplify this you will come across to see that E -1, it is nothing just, it is a linear span of this vector 1 -1. So you got two eigenvector. So you can call this one is the first eigenvector or denoted by V1, and this one is the second eigenvector denoted by V2. So V1 is associated with eigenvalue 5, and V2 is associated with eigenvalue -1. So you are getting two eigenvector of this matrix B1 and B2. So it will form a basis of eigenbasis of, it is forming an eigenbasis of R2. Why? Because 2 by 2 matrix always define a transformation from where to where? R2 to R2. That's way you can say that R2 is the actually domain of the matrix 2 by 2 matrix. So that's way you are getting it. The eigenvector of this given 2 by 2 matrix is forming an eigenbasis in short I will write it E dot B. So it is forming an eigenbasis of R2, and you can say that this it is a eigenbasis for the given matrix. You can say like this way as per the case. Okay, so you have already seen two example. I have even here I am taking one more example here. I will talk about non-existence of eigenbasis. So there is one situation is coming. It is not, I have already mentioned that it is not always possible that every matrix is having an eigenspace, every aspire matrix is having an eigenspace. So one situation is coming here like this way. So if you are taking a 3 by 3 matrix where first row is 1 1 0, second row is 0 0 1, third row is 0 0 0. So if you try to find eigenvalue of this one, it is having two eigenvalue. First eigenvalue is what? 5. Okay, calculation notation I have already changed it here. So it is having two eigenvalue. First eigenvalue is 1 and second eigenvalue is uh, 0. So 0 is having geometric algebraic multiplicity is what? Algebraic multiplicity of this one is 2. It is coming two times. So I would give a notation here, 1 here. Okay. Algebraic multiplicity of 1 is what? It is first eigenvalue is 1. Why? Because 1 is coming 1. So it is very, this matrix, very simple matrix I have taken here. it is upper triangle matrix, so easily you can visualize the eigenvalue. That's why from that perspective I am able to visualize, and I am directly saying that what are the eigenvalue. So we are having two eigenvalue, 1 and 0. So with respect to first eigenvalue 1, we will calculate eigenspace E1. So eigenspace E1 is but it is a kernel of space of A minus I, and if you solve it, it is just a linear span of vector 1 0 0. Similarly, you can find eigenspace with respect to second eigenvalue 0. That one is, we denote it E0. It is nothing, just it is a linear span of a linear span of this vector negative 1 1 0. So you can geometrically visualize this is eigenspace with respect to eigenvalue 0, and this is the, that means it is a line, and this is eigenvector with respect to what eigenvalue 1. So just you are getting only two eigenvector v1, call the this one v1 1 0 0 v1, and call this one v2, second eigenvector v2 associated with 0, and v1 is associated with eigenvalue 1. So we can observe that we are having only two eigenvector. And what here, what kind of operation this matrix is? It is a 3 by 3 matrix. So what is the domain of this one? Domain of this one is R3, and R3 is needed how many basis element? It needed exactly three basis element, but we are having only two eigenvectors, so there is a one sort of basis element, so that's why it will not form a basis of R3. Two vector can't form a basis of R3, not form a basis of R3. So that's why this matrix is having no eigenbasis, not form an eigenbasis. Okay, so you have already seen that there is a there is one sort of eigenbasis vector, so that's why it is unable to form eigenbasis. And there is one advanced concept or advanced part of linear algebra. If there is no worry, if you are there is a one sort of eigenvector, then you can introduce the concept of generalized eigenvector that will fulfill this, that will uh, solve this non-existence criteria. So no worry, in linear algebra always there is a solution. So that one is part of even advanced linear algebra. It is not part of this course. So sometime in future, if I offer such kind of course, then I will discuss. So coming to geometric multiplicity and eigenbasis, what is the relation between these two? So consider an n by n matrix A. If you find a basis of each of eigenspace of A, okay, so what we do? We are having a matrix A, n by n matrix. Then we are finding eigenspace. We are finding eigenvalue. Then after that we are finding eigenspace. If we consider, we take all the uh, that means basis of each individual subspaces, and if we concatenate together, that bring together. What is concatenation? It is saying that it is writing two sequence jointly in together in sequential. So we are not so suppose we are having one sequence, I am calling it with three number, a equal to a1, having three component a1, a2, a3. Okay, and second vector I am taking b, that one is also having coordinate like this, three coordinate, or suppose two coordinate. So call it b1 and b2. Okay, then what is a concatenation of A and B? Concatenation of A and B, that means we jointly will write it A comma B. It is what? It is a five-dimensional sequence. So we will write it like this way. It is five-dimensional vector. First A is written here first. So first entries of A will come. That means A1, A2, A3, A4. There is no A4. Then B is coming. When A has been increase of A has been exhausted, then B will come. B1, B2, and only B1 and B2 are we are having. So you know all these concepts. Okay, this one is a meaning of concatenation. Okay, so what we do, we are having eigenspaces, and every eigenspaces is having basis, and we will jointly write those basis, and we will try to see it will go up to S. Suppose S is a total number of uh, eigenvectors, individual eigenvector, then definitely it these would be what these v1 v2 up to vs, it would be linearly independent. Why? Because these are coming as a basis element, so that's why it would be linearly independent. First criteria. Second, so S is what? You can say that S is sum of geometric multiplicity, because these are all coming as a basis of corresponding eigenspaces. So that's why S, you can call it, it is the sum of geometric multiplicity of the eigenvalues of A. Okay, so there is one more concept, that there exists an eigenbasis for n by n matrix if and only if the geometric multiplicities of the eigenvalues add up to 1, add up to n, sorry, it is add up to n, then that means s equal to n, that means sum of all the geometric multiplicity is equal to n, that means size of the matrix, then you can say that that matrix is uh, what you can get eigenbasis, then that matrix is having an eigenbasis. So one simple example I have taken here. uh, this matrix you can look into, this one is what it is upper, intensely I have taken 5 by what is that, it is 6 by 6 matrix, and it is having, it is upper triangle matrix, and if it is an upper triangle matrix, then easily you can visualize eigenvalue of this one. And there is one criteria I have already written. So if a matrix is having all distinct eigenvalues, then it is very easy to find, definitely that matrix will have uh, eigenbasis. So here you can observe that. So what are the eigenvalues? So I'm just writing for simplicity. I'm not writing the largest eigenvalues first. We are writing just going through in a simple order. So first eigenvalue I am calling it 1. Second eigenvalue is what? 2. Third eigenvalue is 3. Fourth eigenvalue is what? It is 4. Fifth eigenvalue is what? 5. Sixth eigenvalue is 6. So we are having total 6 number of eigenvalue, and all are distinct, all are different. So that's why we can say that this matrix is having an eigenbasis. This matrix is having an eigenbasis. So coming to diagonalization, so what does it say? I have few minutes. So I will revisit the example in order to get a better picture of diagonalization. What does it say? So consider we are revisiting previous example. One of the previous example where we had taken a 2 by 2 matrix having first row 1 2 and second row 4 3. And what was the eigenvalue of this matrix? So it had two eigenvalue. First eigen, so call it E1 equal to 5, or you can take it like this way. I'm not changing the order, so whatever. So I'm taking list as per rule. So even I have taking as a eigenvalue uh, -1. So it is having two eigenvalue. One eigenvalue is uh, -1, and second eigenvalue is okay. So I'm calling it lambda 2. So E5. So try to find eigenspace with respect to eigenvalue E5. It is what? It is just a linear span of the single vector. And eigenvalue with respect to second first eigenvalue -1. It would be what? It is a linear span of this 1 and -1. Okay. So what we observe that, so we can say that this we it is a 2 by 2 matrix, and we have already two eigenvector. One is 1 2, and second is 1 minus 1 2. So even you can call it, this one is v2 and this one is v1. There is a meaning of why there is no, actually there is no effect. If you change the order, it won't affect much. So I'm calling this one v2, this one is v1. So we are having a eigenbasis for this given matrix. Why? Because A is a 2 by 2 matrix, so definitely it will define a linear transformation from R2 to R2. So that's where we got eigenbasis, because of existence of two eigen vector for the given matrix. Okay. Now what we do? We are talking about change of basis. So our standard initially our basis was a standard basis having entry basis element 1 0 and 0 1. Now we are having another candidate of basis. That one is coming as a eigenvector of the given matrix. So it is so this we will take as a basis. So our new basis b beta b, you can say that it is having two vector, 1 minus 1. Clearly it looks that it is a non-standard basis, but it is coming from eigenvector of the given matrix. That's why we will call this basis eigenbasis. Okay. So if you try to find matrix of the transformation with respect to this eigenbasis, what would be matrix? Matrix would be simply a diagonal matrix. It is a diagonal matrix. So this matrix B is actually, you can say that it is a matrix of transformation, same transformation with respect to I'm calling it notation. This not I'm changing this notation. It is B, but it is a little bit scripted B, and this B is what this new basis, notation of new basis. So if you're trying to find a matrix of this transformation with respect to eigenbasis, then what does you will get? You will get a matrix which is actually diagonal matrix. So diagonal matrix very simple. It looks very simple to visualize, and also operation wise it looks very easy. So you are getting a diagonal matrix with respect to eigenbasis. So it is a very general concept that if you are finding matrix of a given transformation with respect to eigenbasis, then that matrix would be always a diagonal matrix. That concept we are calling it diagonalization. Okay. So note we have already seen that B is a diagonal matrix. So I'm just giving a proper definition of diagonalization. What is that? So and also I will say that we are trying to find matrix of the transformation with respect to eigenbasis. It is the another name of diagonalization. So consider a linear transformation P of x equal to ax, and A is a square matrix. Suppose we are having this matrix A an eigenbasis that we are denoting it by D, this scripted D, having v1, v2, v3. v1 is the first eigenvector and vn is the last eigenvector of A. Then what will happen? We will see a relation TVI equal to VI. Why? Because VI is our eigenvector. So from the definition of eigenvector, we will see this relation. Then the matrix of T with respect to this eigenbasis would be what? It would be a diagonal matrix, and the relation between actual matrix of transformation with respect to standard basis and this diagonal matrix, we can see it like this way: D equal to S inverse AX. What is S here? S is the change of basis matrix. Also, you can say that, or where column of S is coming from eigenvector of the given matrix. So this is the relation. So clearly you can say that the matrix diagonal matrix D and a matrix which is having eigenbasis both happen to be similar to each other, similar to each other. So that is the concept of diagonalization. So an n by n matrix is called diagonalizable if A is similar to some diagonal matrix. So we can say that diagonal matrix always we are getting with respect to eigenvector, eigenbasis simply. So that is if there exists an invertible n by n matrix as such that we can always say that S inverse AS is diagonalizable. So I have taken one example here. You can see that. So we can say that matrix is diagonalizable if there exists an eigenbasis of A. So existence of eigenbasis of a given matrix, it always implies that matrix would be diagonalizable. So here we are having two matrices, two by two matrices. One matrix is having first row 1 0 0 1. So easily we can see that it is having only one eigenvalue with its algebraic multiplicity 2. So this matrix is diagonalizable. Why? Because this matrix is having eigenbasis. But if you take this example, second, it is a 2 by 2 matrix. This one is also having eigenvalue 1 with algebraic multiplicity 2. But what is happening? This matrix is not diagonalizable. Why? Because this matrix is not having eigenbasis. So that's why this matrix is not diagonalizable, but this matrix is diagonalizable. So it is. I have taken both kind of example. Other things we will discuss in next class. In last, that would be actually last class. And if you are having any further question, you can put there in the Google Classroom. And regarding attendance, go and mark attendance there in the Google Classroom. I have already created